Okay, this is lesson 1.4b. We just learned about theoretical yield, actual yield, and percent yield. In this problem, we're going to apply a lot of the stuff we've been learning over the past few days. I'm sitting outside, so if you hear the occasional dog barking or horse whinnying or bird chirping, that's why, but I think you'll be able to hear me. So in this problem, we have an iron ore sample that contains iron Fe2O3 plus other impurities. And let's just stop and, for fun, write how we would write the name of Fe2O3. Fe2O3 is iron with some charge, oxide. That'll go down here. And we're going to figure out our charge the easy way here. This 3 over here tells us there has to be a plus 3 charge on the iron. So this is iron 3 oxide. That was an aside. So anyway, we have this iron ore sample that contains iron 3 oxide plus other impurities. So it's not only iron 3 oxide in there. Wait a minute. A 752 gram sample of this impure iron ore is heated with excess carbon, producing 453 grams of pure iron by the following reaction. Iron 3 oxide plus pure carbon makes pure iron plus carbon monoxide. What is the mass percent of iron 3 oxide in the original impure iron sample? Assume that iron 3 oxide is the only source of iron and that the reaction is 100% efficient. So we get to assume that it's 100. It's theoretical and its actual yield is 100%, even though that wouldn't really happen. Okay, so the first thing we're going to do here, this seems to me to be a complex problem. So when I have a complex problem, I write down my information that I'm given. I am given that I have 752 grams of an impure iron ore. So where would I write that? Well, there's no impure iron ore in this equation. Okay, this right here is pure iron oxide. This is pure carbon, pure iron, and pure carbon monoxide. But I have a sample of something. I'm going to draw a picture. I highly recommend that you draw pictures, especially when you're solving complex problems. So I'm going to draw a rock, which is my iron ore. It's my rock. And I'm going to label it as being 752 grams. This is a 7. And I'm going to call it impure iron ore. And just to be super clear, since this is a teacher video, that means that part of it is Fe2O3 and part of it is impurities. Now, I'll tell you, this problem that we're doing right now was a problem on the test for Unit 1 last year. And many people put this 752 right here. They said, oh, 752, they saw iron ore and they labeled it here. But the 752 refers to impure iron ore. So it's a mixture. So this word is very important. It means that the iron ore, impure, means that it's mixed with something else. It's not pure. Okay, back to writing down what we have. It's heated with excess carbon. That tells me that my carbon is my excess reactant, so I'm going to have plenty of it. And that will produce 453 grams of pure iron. So this is my pure iron in my reaction. So I can just, for right now, write that I have 453 grams of this, just as a notation. Okay, then it asks me, this is important, this is my question. It's asking me what is the mass percent of iron 3 oxide in the original impure iron sample. So that tells me I'm going to want to find out what the percent of this is in this overall sample. And I do have an equation that tells me mass percent. I'm going to jot it down. I know that mass percent equals the mass, where's my pen? The mass of the part that I'm interested in over the mass of the whole thing. times 100. I times it 100 because percents are proportional to something over 100. If you have a problem with that, come see me for extra help. So, the mass of the part that I'm interested in, oopsies, this part, the iron 3 oxide. So the part that I'm interested in is the mass of the iron 3 oxide. The mass of the whole is the mass of the whole rock. I'm interested in what is the mass of this, the pure iron 3 oxide relative to the mass of the whole sample. So this is the mass of the whole rock, or the whole sample, times 100. Now, I can go back, so now I have an equation. This is what I'm looking for, this mass percent. That's what I'm asked to find up here. And I have an equation describing how I can get it. So I've looked at my problem, I wrote down information that I had, and I wrote down an equation for what I was looking for. Now I'm going to look at what I wrote for what I'm looking for and see how much of that information I can fill in. So I do not know, there's no number written over here, I do not know the mass of the iron 3 oxide in the sample. However, I do know the mass of the whole sample. That was given to me at the beginning. I labeled it over here. That's the 752 grams of impure iron ore. It's the mass of my rock. So I do know that, so I can write this is 752 grams. I know this. I'm trying to find out this. I know this. I don't know this. I have two variables. So if I can use this information up here to work backwards to figure out what the mass of this is, I'll put a little question mark grams, then I can, that's a question mark, and then I can fill this in, then I'll be able to solve for mass percent. So that's what I'm going to try to do. I'm going to try to work backwards from this information, probably using a BCA table to get to this information. Okay, so I've created a BCA table, before, change, after. I retyped the equation. Ignore these little periods, I don't know why they come in here. I typed it so it would be more legible in my scribbles. So I know that at the end of the reaction, which would be after, I'm going to have a certain number of moles of iron. And I can figure that out because I know I'm going to have 453 grams at the end of the reaction. So 453 grams of pure iron. I can calculate how many moles that is, and I only put moles in my BCA table. If I multiply by the molar mass, for every 1 mole of iron, I have, let's look on the periodic table, in every 1 mole of iron there is 55.85 grams of mass. I can use that to figure out how many moles are in 453 grams of iron. It'll be more. And in 453 grams of iron we will have 8.111 moles, I'm taking it out to an extra significant figure, of iron. So that's how many I'll have at the end here. 8.111 moles of pure iron at the end of the reaction. Now this problem said it was 100% efficient, so at the end I will have 0 moles of iron oxide. They told us that we had excess carbon, so if it's excess, and nobody's asking about it, I'm not going to care about it. And nobody has asked me about carbon monoxide, so I'm just going to ignore that for now. What I want to find is how much of this I had before. So I'm going to draw a little purple line or a box over here. Let's think about how we could find out what we had before. Okay, this is how much pure iron we have after. That was created by a change, which had to be plus 8.111 moles. And before the reaction started, we had 0. Whatever this change is over here, whatever was added here is related to what was used up here. So I can figure out that relationship, and that'll tell me how much I had up here. If I used 8.11 moles here, how many moles of this did I use up? Well, for every 1 mole, I'll just put a little 1 here, of iron 3 oxide I used up, I made 2 moles of iron. So this is a 1 to 2 ratio, or 2 to 1. So let's figure out how many of this we had to use up if we made 8.11. We can actually do it. We don't want to do it on our head. We can do it here. 8.11 moles of iron. Multiply that by a molar ratio. For every 2 moles of iron that were created, 1 mole of iron oxide was used. And that ratio will allow me to figure out, if I divide 8.11 by 2, so that's what this is telling me, this multiplied by 1 divided by 2, I will find out that I had to use up 4.0555 moles of iron. So this had to be minus 4.0555 moles of iron. And if I subtracted and got 0, I had to start with 4.0555 moles of iron. So that's how many moles of iron were right here, over here, 4.055. I needed to find the mass. Remember, this was a question mark. The mass of this, I've found the moles, so now all I have to do is convert that to grams, and I can put it in here and solve. I think we should do that on another, well I'm going to scribble it in here. So, if I have 4.055 moles, actually we'll just go to the next page. 4.0555 moles of pure iron, nope, not pure iron, Mrs. Irwin, of iron 3 oxide. What is that in grams? Well, in every 1 mole of iron 3 oxide, what is my mass? How much mass do I have? Let's figure that out. We have 2 irons, that's 2 times 55.85, 111.7 grams, 3 oxygens, they add up to, hopefully, 159.7. So for every mole of iron 3 oxide that we have 159.7 grams. That's my molar mass ratio. I can use that to figure out what mass I would have if I had 4.055 moles. And that ends up being, if you multiply 4.055 times 159.7 divided by 1, you get, I think you get, 647.6 grams of iron 3 oxide. And if we remember on the previous slide, we had mass percent was equal to the mass of the iron 3 oxide, which we now know is 647.6 grams, divided by the mass of the whole rock, which was 752, I hope. This was the impure sample, the whole thing, multiplied by 100 equals 86.117, so I'm going to round to 86.1%, 3 significant figures. That is our mass percent of the iron 3 oxide in the rock. So, this was a complex problem. We solved it working backwards. You have a similar problem in your homework problem set. I can't remember the number, but it deals with sodium nitrate and sodium nitrate. Okay, that is it.